Welcome back. Let's look at some inspiring PV applications. The learning objective of this video lecture is simple: to get inspired by some PV integrated systems which might exhibit multiple functionalities that go beyond the residential and onshore large-scale utility application of PV systems. From photovoltaic point of view, there are four main factors influencing the output of PV energy yield. First, the source of energy, the sunlight, the converter, which is the PV cell or module, then the amount of time that the PV unit can work or operate, and finally the amount of area that the PV technology is added on or integrated into. In this video lecture, I want to put more emphasis on the area, the surface that the PV system is implemented on. We will discuss some inspiring PV system applications beyond the traditional residential large-scale utility applications. In most large PV projects, the solar modules are deployed in wide open areas such as deserts or plains. Here you can see the satellite image of the Batla Solar Park, the biggest photovoltaic installation in the world. The massive PV power plant with a capacity of 2,245 megawatt is installed in the Thar Desert of Rajasthan in India. But are desert or wide large plain the only places that we can put PV on? PV has applications in many other areas. We can look around us in a way that each surface has the potential to produce electricity through the photovoltaic effect. Whether it is a road surface, a roof surface, or a building facade, or even a water surface or a canal. Not only roads, but the surface of the cars moving on the road, the canals, and the surface of the vessels cruising in them. Each surface comes with its own unique features, so when we say we aim for PV everywhere, we must be ready to face new working features for the photovoltaics. Photovoltaic panels not only are used for the generation of clean electricity and reduce energy bills, but also can be used for several other purposes. They can protect animals from hot weather waves, can homogeneously distribute light on croplands, can prevent water evaporation behind dams, can increase the driving range of vehicles, or even bring visual attraction to the buildings, etc., etc. Integrating photovoltaics into various surfaces brings multifunctionality, meaning that the surface can be used for other purposes alongside generating clean electricity. A PV panel on the top of the water behind an hydrolytic dam benefits from the cooling effects of the water while preventing water evaporation, and as a result increase the potential of the dam for generating energy through hydraulic turbines. Adding bifacial PV panels on top of a farm or an orchard can increase both the productivity of the crops and the PV panels. PV panels on top of crops, if designed smartly, can be used as irradiance diffusers to homogeneously distribute the light on the crops, while the reflection of the light from the crops can boost the PV performance as well. Some crops are in favor of occasional shadows and some are not. Photovoltaic cells on the roof or the hood of electric cars increase the driving range of cars as well. Solar panels are also being deployed on water areas, inland and offshore. A floating PV plant normally consists of floats, mooring and anchoring systems, PV modules and balance of system components. This figure shows a schematic of a floating PV plant and its key components. Except for the floats, which bring the necessity for mooring and anchoring system, the rest of the floating PV plant is almost the same as a ground-based installation. Floats are compartments with buoyancy to keep PV modules and supporting structures float on the water. Floats should be recyclable, non-toxic and resilient to water, salt corrosion and UV radiation that can ensure more than 20 years of operation with minimum effect on the water body ecosystem. There are three types for floats used for floating PV plants. The pure float with high density polyethylene, the HDPE material, pontoons or hollow cubes with metal trusses, and special membranes or mats. Mooring refers to any permanent structure which is used to forestall free movement of the floating structure. An anchor mooring fixes a floating structure's position relative to a point on the bottom or the sides of a water body. This will prevent the floating PV plant from being blown or pushed away by wind, load, wave force and other water streams or hit the banks when the water level is changing. Examples of three main anchoring types are shown in this slide. The type of the anchor depends on the soil condition. A floating PV can also have a combination of different anchoring types. The yearly power production curve of a hydropower plant is mainly governed by water seasonal cycle, which is complementary to the sun irradiance cycle. Therefore, the hydropower plant and the floating photovoltaics can work complementary, while the floating photovoltaics is benefiting from the surface of the calm water behind the dam and the already established grid infrastructure. And on the other hand, the hydropower plant benefits from less water evaporation and complementary power production profile. Also, with a coordinated control of the hydropower plant and the floating photovoltaics, can work together to provide stable power without the need for electrical storage. A recent research studied the 20 largest hydropower plants across the world and concluded that by covering 10% of the hydropower plant basin surface, the hydropower plant's energy production is increased by 65%. The figure shows the hybrid hydropower plants and the floating photovoltaics capacity around the globe. Agri-photovoltaic is a concept that originated from the 1980s. It is defined as a land use concept that directly integrates solar energy production and agriculture activities which are practiced under the photovoltaic field installation. Agri-voltaic is a concept that originates from the 80s. It is defined as a land use concept that directly integrates solar energy production and agriculture activities which are practiced under the photovoltaic field installation. Agri-voltaic practices can be carried out in different ways depending on the activities carried out by the population in a given area. Agri-voltaic applications represent the combination of energy production with agriculture production in the field, or agriculture production in the greenhouses, or livestock rearing, or provision of the ecosystem services through vegetation management, or different agriculture practices combined. One performance index used in agrivoltaics is the Land Equivalent Ratio, or LER. LER is a performance index for land use efficiency. Land Equivalent Ratio is the sum of the respective yield ratios of dual land use to mono land use. There are other performance indicators for agrivoltaic as well, such as the light homogeneity under the PV panels. This is assessed by the simulation of radiation distribution under agrivoltaic systems. Active countries in the field of agrivoltaics are Germany, Italy, France, Japan, USA, Taiwan, and Egypt, for example. A comprehensive study on agrivoltaic systems throughout the US, performed by the National Renewable Energy Lab, NREL, identified 5 key parameters influencing the success of an agrivoltaic plant. Let's summarize those. climate, soil and environmental conditions. The ambient conditions and factors of the specific location that are beyond the control of the solar owners, solar operators, agrivoltaic practitioners and researchers. Secondly, configurations, solar technologies and designs. The choice of solar technology, the site layout and the other infrastructure that can affect the light availability and solar generation. Third, the crop selection and cultivation methods, seed and vegetation designs and management approaches. The methods, vegetation and agriculture approaches used for agrivoltaic activities and research. Fourth, the compatibility and flexibility. The compatibility of the solar technology design and configuration with the competing needs of the solar owners, solar operators, agriculture practitioners and researchers. And fifth, collaboration and partnerships. Understanding and agreements made across the stakeholders and sectors to support agrivoltaic installations and research, including community engagement, permitting and legal agreements. PV can also be implemented on moving surfaces such as vehicles. We can either use the area above the hold of bulk ships, take advantage of the free area above the train roofs, or the free area on top of lorries. In this way, the network of vehicles can work as a moving network of distributed generators which have minimum transmission loss due to the vicinity of the generation and consumption. The pros for vehicle integrated photovoltaics are an increased mileage, a reduced load on the electricity grid and charging infrastructure, cost savings for charging electricity, reduction of the CO2 emissions in the transport sectors. The cons for vehicle integrated photovoltaics are it requires new materials and production processes compared to conventional module constructions, different type of modules for the specific application areas requiring individualized production, and high efficiency values relative to the surface areas are required as well. Here you see a nice example of a study in 2021 in the Netherlands, which poses the largest inland shipping fleet in Europe with 8,000 vessels. That could accommodate 267 megawatt of photovoltaics. This graph plots the data over the vehicle integrated photovoltaics commercial offerings and R&D projects. The mean photovoltaic area that cover the vehicle for each kind of vehicle is significantly different. The mean embedded PV area ranges from a couple of square meters for cars to thousands of square meters for ships. Note that although passenger cars have the lowest available surface, they are currently the leading application of vehicle integrated photovoltaics. I hope this video lecture inspired you. In summary, you were introduced to some PV integrated systems that go beyond the residential and onshore large-scale utility application of photovoltaic systems. In addition, it was shown that PV systems might exhibit more functionalities than only generating renewable electricity. Next week we are going to discuss several financial and circular concepts of photovoltaic systems. So see you back in the next video lecture.